Okay, today's lecture we will continue on convolution, and we will go, last lecture was introduction to convolution and properties about convolution, while today's lecture we will do more in calculation of the convolution. So, today is February 5th, Monday. The readings were from page 40 to 58. So it will be calculation convolution, and it is the due date for homework number 4. While in Wednesday, it's the deadline for project MATLAB project 2 on homework number 5. So no submission on homework 5. And also, in Monday, there will be no lecture. Okay? No lecture, no recording, so don't worry about it. I have some business work, so, and also, we have a good progress, so I don't need to record a pre-recorded lecture. So we can skip Monday, then we skip Wednesday. But remember the deadline for the MATLAB project, so it's still on Wednesday. And you can take this opportunity to review the classes for the test. Friday, the readings are from page 40 to 58 as well. Then in February 12th, next week, Monday, most likely it will be review for test, for example. So until Friday it will be covered in the test, while Monday will be only review. Then the tests will be 14 Wednesday. So exam 1. And it is an hour of lecture time, which is between 10 to 10:50. Try to come 5 minutes early so we can start earlier than 10. It will end exactly at 10:50. Okay? So the exam will be until the end of convolution. So convolution we will start, we already started last lecture. So today we will do more calculation, and even in Friday lecture, we will keep calculation about convolution. Then for Monday, will be review about overall thing. And most likely on Monday, I will go through one of the sample exams. So I will go through the sample exam. Yes.
Are you going to post the sample exam?
Yes, I'm going to post it and post the answer. So it should be available. So when you have the sample exam, then you can have a clue how the test will be. So it will be, I think, much easier for you to understand how the test will be. Okay, so last lecture, we discussed about the differentiation, and we mentioned about the derivative. So the overall, something we call it ideal differentiator. Ideal differentiator, which is for the derivative of delta. d by dt of delta of t, or in other words, delta prime of t. So we have here x of t, then delta prime of t yields to the derivative of the signal. That's what we mean by ideal differentiator. So we can make any integrator, any differentiator, any time shift delay using the logical signals by using, we have delta, we have u of t, or delta of t minus tau, whatever we need. And basically, this signal means x of t, according to our signal, convolution convolved with delta prime of t, or in other words, x of t convolved with the time derivative of delta of t, and according to the derivative, this can be d by dt of x of t convolved with delta of t. That's the derivative property. Then it will be d by dt, x of t convolved with delta of t is x of t according to the properties. Then that's how we get it. This is the okay? Now keep in mind, whenever we have x of t, then we have delta prime of t, then here h of t, this equivalent to dx of t by dt convolved with h of t. How about if we make x of t, then we put h of t, then here we have delta prime of t, so here the first thing, x of t convolved with h, then do the derivative. So it will be d by dt of x of t convolved with h of t, or whenever we have h of t, or h of t, then here delta prime of t, then we have here x of t, this is equal to d h of t by dt convolved with h of t. Now, all of these three blocks, we see like different expressions, different outputs. But according to LTI system, the order shouldn't matter. So they are all must be equal to each other. So all of them are equivalent. Which means this term equal this term equal this term. And this is again the same as our derivative principle, which is basically whenever we do the derivative for the convolution d by dt of x of t involved with h of t, when we distribute the derivative, put it at only one of them. So it can be either d by dt x of t convolved with h of t, or it can be x of t involved with the derivative d by dt of h of t. So all of them are the same. So all of these three scenarios are the same. And you can see that it's again an LTI system, so whenever you swap any of those, this should be the same. This is the properties of the LTI system. Clear? So in summary, derivative, which is x of t convolved with delta prime of t, this equal to dx of t by dt, and it is like this. Here is delta bar of t, delta prime of t, then here is y of t, here is x of t. Okay? And it is called ideal differentiator. And then we make the equivalent circle like this one. This is equivalent to ideal differentiator. Equivalent to this, which is just make d by dt. Okay? Second thing, the normal thing, which is normal situation, or nothing, which we say like nothing. Whenever we have x of t, convolution with delta of t, this is equal to x of t. So do nothing. It looks like you put x, put delta of t, but without prime. Keep in mind the first, that one was with prime, now here is no prime. So it will be y of t, which is equal to x of t. And this is equivalent to short circuits. Okay? That's the second scenario. Third scenario, delay. Time delay. Time delay, whenever you have like x of t, delta of t minus t0, then here y of t equals to x of t minus t0. And it looks like the same function, but we'll put delay. Delay by t. Okay? Number 4. doing, we have differentiation, delay, now integration. Integral. So the integral, by doing u of t, so we will put, we have x of t here, then u of t here, here is y of t, which is the integral from negative infinity to t, x of tau d tau. So this is ideal integrator, that will be integral. Now, the other thing, which is double integral. So double integral by making r of t. So here I forgot to write the time delay x of t involved with delta of t minus t0 equal to x t minus t0. Here for the integral, x of t involved with u of t equal to the integral negative infinity to t x of t x of tau d tau. Now double integral means when we have r of t, so x of t involved with r of t, this is actually equivalent to x of t involved with u of t involved with another u of t, which yields to the double integral negative infinity to t, negative infinity to t, x of tau d tau. And this is equivalent when I have here is x of t, here is r of t, here is y of t, equivalent to integral, first integral from negative infinity to t, negative infinity to t, and that's it. So now, using these inputs, we can do differentiation, we can do integration, and we can do, and by making the convolution as well, differentiation, integration, double integral, the normal situation, or time delay, or the buffer, which is, or short circuit, or time. Okay, so, yes?
And then it doesn't matter the order we do these operations in?
The order like what?
Since it's all convolution, it doesn't matter how we apply these operations.
I didn't understand this, I'm sorry.
Does it matter if we do a double integral before we do like a time delay?
Yes, yeah, it doesn't matter. Yeah, because here, like as we said, like it's LTI system, so the order should again, like this can be yes if and only if LTI system. If it's other than system, other than that, it doesn't matter.
What's inside that double integral system?
Here?
From the t
Negative infinity to t.
before that. This is not that system, yeah.
This is equivalent to t. So
What
we
is
would
the
say
symbol
this is
before t?
x of t. Yeah. Here is y of t.
That's
In the first
In the first here, r of t.
art.
Any question? Let's do some examples to see if how we can apply these concepts in our system or in these concepts in our understanding. Example number 1. So let's assume we have x of t here, then there is delta prime of t, u of t, another u of t, then y of t. Our target is to calculate what's y of t. According to our analysis, y of t is x of t convolution with delta prime of t, convolution with u of t, convolution with u of t. Is this correct? That's our analysis. So x and delta prime, this is equivalent to dx of t by dt, and convolve the u of t, convolve the u of t, right? Then u of t and the derivative cancel each other, integration and derivative. So the output will be x of t convolve the u of t. Now we have x of t and u of t, apply integral to negative infinity to t, x of tau, then that's it. Okay? So this is the overall system. So just apply the knowledge that you know from x of t and let's do another example. Here we have x of t. It will go to different things. So we have here u of t. Then that u of t will go to delta of t plus 1. Then it will go to a summer. Sum. Then on the other side here is delta of t. It will go to u of t, then subtraction, then here we have y of t. And this is all of it inside the box. That's what's happening inside the system. Now we need to find two things. The first thing, find y of t. The second thing, find impulse response. Now, the first thing, we need to find y of t. So you can look at the system here, follow with x. X goes here, x goes here, right? Then x, there's u of t, so it will be then the integral of x. Is this correct? Then we have delta, this means the integral of x t minus 1, because t plus 1 actually, because we have a phase shift. Delta alone, nothing, but when there's plus 1, t plus 1 means there is a phase shift. Okay? So we have integral with phase shift. This is the first, the top side. The bottom side, x, and we have delta remains x, then we have u, the integral x of t. So there is sum and addition. So in summary, we will say for number 1, it will be the integral between negative infinity to t, x of tau plus 1, d tau minus the integral x of t, which is x of tau, integral negative infinity to t, x of tau, d tau. Okay? Is this clear? That's the first thing. Second thing, we need to calculate the impulse response. What we mean by impulse response, replace every x of t by delta of t, every y of t will be as h of t. That's the impulse response. So you have an option to use the answer that you did in number 1 and substitute them here, or you can go back to the original circuits. So there is method 1. Method 1, by using the output that we get. So we have replaced by y of t by h of t equal the integral negative infinity to t. X of t will be delta of tau plus 1, d tau minus the integral negative infinity to t, delta tau, d tau. The integral of delta means u of t, so it will be u of t plus 1 minus u of t. That's method 1. But again, method 1, by substituting in the expression that we got in number 1. Or, you can use method number 2. Method 2, basically, I'm going to go back to the original circuit and try to do the analysis other than following y of t. If, for example, there is no question find y of t, if just the question side says find the impulse response. So what should I do? go to the circuit, and I'm going to put the impulse as bottom here, delta of t. So here is delta of t, here is delta of t. Delta, and there is integral for the delta. This means it will be, the integral of delta is y, is u of t. Here, delta of t and delta of t will be then delta of t. Then we have a phase shift t plus 1, so it will be u of t plus 1. And here there is integral, so it will be u of t. Then it will be y of t, which is h of t, will be u of t plus 1 minus u of t. And that's it. So this is another way. So this will yield h of t to be u of t plus 1 minus u of t. So let me show it to you again, and if you want to write it about it. Okay? Yes,
Just go down a little bit, please.
now, for this question, I want you to try it at home. Here. Try it. Which is, calculate the impulse response. I'm sorry, the step response. The final answer, y step, will be what? Try it. Substitutes x of t by u of t, and y of t will be replaced by y step of t. Try for the problem here. What do you think the answer will be? The top will be so here, this is u of t. U of t, we will do integration, will be r of t. R of t with phase shifts, r of t plus 1. Right? Then the bottom, here is u of t. With delta, u of t. Then integration, r of t. So, this yields to y step will be r of t plus 1 minus r of t. Good. So, I can write it here as r of t plus 1 minus r of t. Ready for the next example? No. Now we need to first thing find y of t when x of t equal delta of t minus 1. The second thing, find step response or impulse response. Okay, what's the system? Here is x of t, similar to the system of assumption. Right. Here we have delta of t plus 1. Then we have u of t plus 1. Then we have a summer here, will be positive. The other parts, here is a multiplier, when there's a process multiplier, and we multiply by 3, equals 3. Then we have here u of t, so we'll go here, and then this is overall what's happening inside the system. Then we have here y of t. So the first thing, we need to calculate y of t when the step response is, or when x of t is delta. So I'm going to write this in red color. So we have input is delta of t minus 1 x of t. Here is delta of t minus 1. Here is delta of t minus 1. The first thing we have on the top, there's a shift plus 1. T minus 1 plus 1 minus 1 plus 1 will cancel each other, so there will be delta of t. How about 3 times delta of t minus 1? It will be here 3 times delta of t minus 1. Then we have u of t. Then we have a shift and integration. So it will be u of t plus 1. And the other side, there's integration. And it will be 3 u of t minus 1. Then there's a sum. So number 1, y of t will be the top, which is u of t plus 1 minus, it's both of them are positive, so it will be positive, plus 3 u of t minus 1. Okay? Does this make sense? Second thing, find impulse response. Impulse response will be denoted by h of t. Notice the first one, even though the input is delta, but it's not delta t, it's delta t minus 1. So it's not considered as impulse response. Impulse response, if and only if input x of t equal to delta of t alone, without something else. So to find impulse response, I'm gonna change the color. Here, delta of t. This is delta of t. Delta. So we have a shift, delta of t plus 1. Then we have integration, it will be u of t plus 1 plus 1 plus 2. Then in the bottom, delta of t, 3 times delta of t. Then we have integration, so it will be 3 times u of t. Then there will be addition. So as a result, h of t will be the top, which is u of t plus 2 plus 3 u of t. Okay? Does this make sense? It's very crucial to understand this example. Yes?
How did you add the two different functions in this example but subtract in the previous one?
Yeah, that's a good question. So here we have positive, positive. This is something. Go back to the previous example. Positive, negative. So depending on the signs. Any other question? Okay. Now that's how we do the convolution in some simple inputs. But if we have multiple or more complicated inputs, actually this will be more complicated analysis. So sometimes not everything in delta of t or mu of t, sometimes it can be sine, cosine, some other type of signals, which will make it hard to do the integration. So in this situation, what you need to do is, you can use some advanced techniques of the analysis, which is like the advanced technique of differential equations, or using the integration a lot. This kind of integration might be too complicated, which will make it unsolvable in some situations, or very hard. This is called entanglement. Therefore, in order to satisfy or to overcome this, we will learn this actually later, which is something that's called frequency domain. Because in time domain, there's a lot of integration, but when we do it in frequency domain, it will make the life easier. As we will learn later, that's why do I need to do, do I need to do this for the rest of my life? Doing integration, doing these convolutions, or convolution is complicated because of the math. The integration of it is math. It's complicated. So just let me write as you know, the convolution, y of t equal x of t convolved with h of t. So then we have here the integration from negative infinity to infinity, x of tau h of t minus tau d tau, or it can be the integration between negative infinity to infinity h of tau x of t minus tau d tau. So we need to calculate first the impulse response, then we need to do the integration. So which will make it again difficult to do. Why? What we learned in the properties last lecture and even in these examples that we discussed, very simple situation by assuming delta and u. But in real life, not everything like this. This is something simple, and this is just for demonstration. So in real life, a more complicated thing, how to overcome these situations? By going to the frequency domain. Frequency domain, this is something that we will do later, but now, for this course on perspectives, in order to prove the concept, we'll assume some situations or some functions that can be integral or we can do the analysis. Okay? So something similar to this, something that we can do without spending 1 hour in one example. Now, I have something or else, like other than like this calculation, is something called graphical computation of convolution, which is how to convert the convolution in a graphical way, not equations. So basically, we will have h of t or x of t. So we need to do the convolution between them. How we can do this? Most likely, the waveform of x of t or waveform of h of t will be given both. Waveforms h of t and x of t will be given. So you don't need to worry about this. Now we need to find the plots for the convolution when they are given. So the first step, let's assume we have h of t like this. Here's, for example, 0, here's 3, something like this. So the first step, in order to do the convolution as we know, let's assume that we will apply the convolution as negative infinity, x of t, h of t minus tau d tau. So we need to figure out how to find h of t minus tau using the given h of t. How to find h of t minus tau. So the first step, let's convert x of t, h of t to convert h of t to be h of tau. Just convert the variables. So the time is the function of time, function of t will be function of tau. Just changing the variables. So here is h of tau. Then the same thing, no change in the function. So here is 0, 3, and this is just a this is 1. This is 1. Then what we will do next, which is in order to say t minus tau, let's convert h of tau to be h of negative tau. H of negative tau means mirror. Whenever we say we already have a time shifting property for the function, so it looks like mirror. Here's tau, here is h of tau, so the mirror will be like this, like you are mirroring this. So this is 0, this is negative 3, and this is so mirror on the t tau axis, or in the h axis or y axis. That's what we do. Okay, so we know how to do h of negative tau. Do you agree with me on this, mirror? Now we will convert h of negative tau to be h of negative t minus tau. Right? So we will just put t tau minus t. And actually, when you distribute this, it will be as h of t minus tau. So basically, we will make a shift by looking at this t minus tau equals 0. We will make a shift by tau equal t. And that phase shift will be positive. Tau, here is h of t minus tau. So basically it will be as, let's assume t here like this, then here negative 3 plus t. Okay? So there we will go on this. Now for this plots, actually we have different cases, depending on the value of t. I mean here I assume t like this way, while t can be something large. So if t, for example, I would say less than 0, so the location h of t minus tau will be different. H of t minus tau, it will be if t less than 0, for example t here negative value, and here negative 3 plus t. It will be like this way. Here is the location of delta of t, h of t minus tau. I have another solution. If t is positive, what will happen? I'm going to make it if it is between 0 and 3. If it is between 0 and 3, it will be, for example, here's t, here's negative 3 plus t, and this is the same, h of t minus tau. Here's tau. Now, when t larger than 3, so here's t, here is negative 3 plus t, then it will look like this. So far, when we did h of negative t, everything is good. But when we make t minus tau, there is something that makes it more difficult. Because we don't know exact value of t. T can be changed. And why I choose t less than 0, t between 0 and 3? Because imagine this triangle is moving, shift or left or shift right. So these are the cases that's happening. So it's being shifted. You see this triangle, how it's being shifted? That's something matters with us, which is the shifting of the triangle. This will make something, will make the convolution more difficult. So the first thing after calculating h of t minus tau, then we can, the next thing, plot x of t. Then we have the plot of x of t, assume it's given as x of t, and we'll make it as x of tau. Any waveform, for example, square, whatever it is, it's going to be like this way. X of tau. Then for the convolution, you will put them together and calculate the area. Because we know the integral y of t equal the integral from 0 to t x of tau h of t minus tau d tau is related to the area. Integral means area. So you will see, is there any cross-section area between x of tau and h of t minus tau? If there is cross-section area, then the integral of this area is the convolution. If there is no, then the convolution is 0. Okay, how we can understand this in a graphical way before doing the examples? Go to Canvas, the modules, you will see a link, it's called convolution here. Now let me go here. Let me show you the screen. Go to modules. Convolution table. So here we have x of t, h of t. Here, even though they are called f and g, whatever, but assume the first one as x of t, the second one as h of t. Now we need to do a convolution. So let's assume h of t as, for example, square. Yeah, it's like a square. And x of t is fixed. x of t like this one. Okay? Can you see the screen? Now, we are all on the same page, like this side is called x of t, the blue side is h of t, right? Now, we will make x of t or h of t as fixed, which is something will not be moving, but h of t or the blue thing will be moved. Will be moved like the same way that I showed you in like t minus tau by using the value of t. So, that's the function. That's how the function looks like. X of t is fixed, while h of t is moving. The thing why make it's moving, it's h of t minus tau. Why is it moving? Because we have the value of t will make it different. So if t is, for example, as we see here, for example, -3, then it will be out. There will be no cross-section area. Yields to output will be 0. The integral is the common area, cross-section area. Then, when I move the triangle or reduce the value of t or make the t from negative going to the 0, toward the 0, still cross-section area is 0. Now, you will see something starts to see some output, which is basically, we will start to see some intersections. That intersections, as we see here, this triangular shape, we can calculate the area. That area, or do the integration, that area is the output of the convolution. So you can see in the black is the output of the convolution, so it's 0, then start growing. Look at the black line. It was 0. When it starts growing, when there's some area, you see the area, and look at the black, how black is growing. You see this? Then you see it still keep growing. And since the first half or the first portion of the output is increasing, it will keep increasing until reaching the peak. After reaching the peak, the output will be decreasing. This makes still the area high. Then it's still increasing because the area is still high. Until reaching, this is the maximum area that we can achieve. Then the area will start to be reduced. Therefore, the black line is going down. Then going down. As we see here. Then, when there will be no area, it will go to 0. So the output here is 0. Then we move here, there is no intersection, then 0. So in this situation, you will see how the overlap will happen. When there's overlap, there will be output. Look at the cross-section here. And the good thing about this software, you can do different output. Let me make impulse function. Let me make like train impulse or sawtooth signal. And here let me use square. Then you can fix one and move the others. Then you can do whatever you want with this. And you will see the outputs. Okay? So I think understanding this is something very important. So you will, whenever there's no area, it is 0. Then when it's moving, it will be different. Again, which one is moving? That I'm assuming h of t is moving. And why it's moving? Because I assume it as h of t minus tau. Then the value of t will matter, so will make the situation change. Because we don't know exactly what's the value of t. It can be any number between negative infinity to infinity. Then that's how we do the analysis. Most likely we will look at where there is some overlap. So we will say before this time it is 0, then at this time it will start growing, then at this time it will start decaying, then this time we're back to 0. So there will be 4 cases. For when it is 0, first one when it is 0, second one when it starts decreasing, the third one when it starts decreasing or because of whatever, and then the fourth one when it's go back to 0. That's what we will do every time when we do the convolution. Let's go back to the notes and try to apply this in equation or like, not like this software. Let's try to do it by ourselves. So as an example about the convolution, again, in this example, x of t and h of t are given. So you don't need to worry about this. It can be either given as function or it can be given as plots. So for example, I'm going to assume x of t equal u of t, h of t equal u of t minus u of t minus 1. This is equivalent when we do the plots. X of t Then when we do u of t or h of t, h of t it is at t equal 1 go back to 0. So 0 to 1, h of t. And here is, let's assume the value. Now we do the convolution. Let's recall, when we do the convolution, we will convert everything to be x of tau and h of tau. So let's do this as x of tau, the same thing, but it will be x of tau. And here for this one, we will do h of tau. H of tau. And my target is to convert h of tau to be h of negative tau, then h of t naught minus tau. So this one, because h will be changed while x will remain. So here, h of negative tau will look like this. Here is 0, here is negative 1, this is 1. Then we want to do h of t minus tau, h of t minus tau, then it will be like, here's t minus 1, and here's 1. Now, my concern is x is changing, t is changing actually. T is changing. So we have several situations. The first situation, let's try to imagine that t will be like this, then move like this, something like that, then half of it will be like this, then will be like this, something like that. It will keep moving. The same thing when I showed you in the software, which is, it is moving, right? This only h is moving because t is changing, while x will remain as is. So let's start with case number 1. When t less than 0. When t less than 0, we have a negative. Let's plot the two things, h of tau and x of t minus tau. So here, t minus 1, this is how h of tau looks like, h of t minus tau, while x of t x of tau like this. Now, is there any overlap? Any area, cross-section area? No cross area. So, convolution will be 0. So I will say y of t. That's case number 1. Okay? Case number 2, which is when we have between 0, t, then to another range. Another range like what? How can we determine the other range? Let's plot x of tau because it's fixed. Now we need h if it can move like this way. So I will say like t negative 1. So the best scenario here, we will see like some cross-section area. But when will this area end? We will assume because it's half of it, didn't reach completed area yet. When it will reach completed area? When t equal 1. When t equal 1, this will be 0. This will be 1. Then it will be completed area inside the u of t. Is this correct? So it will be completed area at 1. Therefore, I will write t0 to 1. That's what I mean. So how can we do this analysis? Basically, you will say y of t equal the integral between 0 to t, x of tau, h of t minus tau, d tau. Now, x of tau during this area is equal to 1 times h of tau t minus tau equal to 1 d tau. So the answer will be the integral to 1 from t to tau. Then it will be t, since t equals 0, u of t. That's the second thing. Now the case number 3. When t larger or equal to 1, this yields to, I'm going to plug it, x of t, like this, and we have h of t minus tau, like this. So all of the area happened here. Here is h of t minus tau. This is x of tau. Then there will be yields to y of t equal the integral between t minus 1 up to t x of tau, h of t minus tau, d tau. So it will be the integral 1 times 1 d tau between t minus 1 to t. So it will be an u of t, 1 times u of t, which is u of t. So the overall, there is no other things. These are all 3 scenarios. Then y of t will be 0 and t less than 0 will be t, u of t when between 0 to t to 1, and it will be u of t when t larger than 1. This yields, if we need to plot the output, this yields the output to be as y0. Then here start up at 1, 0 to 1 is u of t, and this is 1, so this is y of t, which is the convolution x of t convolution. That's one simple example. The next lecture we will do more about examples about this. See you on Friday.